All right, back. I just finished calculating the lower bound in the case where we were looking at rental cars. If you recall, the problem, we had a sample size of 200. We had a sample mean of 325, and we were assuming we knew the population standard deviation was 60. We want to know what the 95% confidence interval is, and so we calculated, calculated the sampling distribution standard deviation, and then we showed on a graph here the problem we were trying to solve. We were trying to find mu1, which is the lower bound, which is the population mean for a distribution in which our sample was weirdly high. Right? That's what that lower bound is. If our sample is an outlier, or just on the edge of being an outlier, it's not an outlier, but it's right on the tip, what's the true value of the mean? And we found that if our sample was an outlier in the upper tail, that meant that the true mean was mu1, which was 316.7. We can do the same problem to find mu2. The way this works, I'll just set this up like a straightforward problem. I won't redraw the whole thing. Let's see, let's imagine we have a sampling distribution that looks like this. It's centered at mu2. It's shaped the way the other one was, so the standard deviation of the sampling distribution is 4.2426. That's 4.2426. Well, this mu2 is the mu2 that would make our sample mean 325 an outlier on the bottom tail, just barely. In particular, what we mean is because our alpha is equal to 0.95, it's the one that would make this big area in the middle 0.95. So that's the question. What's the value of mu that would make 325 be right on the tail? Right on the tip, right, just not quite in the tail. Well, because it's symmetric, we can cut this in half again. This is 0.475, and now we can relate it to the standard normal distribution. So we draw another distribution down here. That's terrible. Oops, daisy. There we go. Draw another distribution, like so. I apologize, I need to get better about drawing my standard normal distributions. Anyway, 0 is here, 1 is here. Draw a dotted line. This is our value of z. And this area right here is 0.475. To find that z, we look it up on a table. I use a 0 to z table, but 0 to z tables only show positive values of z. If you look up 0.475 in the body of a 0 to z table, what you'll find is that that corresponds to a positive value of z equals 1.96. We already did that for the first half. That means that this z is going to be negative 1.96. Okay. So in order to solve this, we take this and we use our score function to back it out. Let's see, I'm running out of space, so let me get us some more space here. Okay. So we have our z value. We can use our score function to back out our mu. That's what we really want to do here. So let's pick a color. We use orange. Z equals x bar minus mu x bar over sigma x bar, which in this case is, we can plug this in, negative 1.96 equals 325 minus mu2 over 4.2426. Alright, so we need to do a little bit of algebra. First, we're going to multiply both sides by 4.2426 to cancel out the division. So you see a fraction, getting rid of that first is always a good idea. So this times negative 1.96 is equal to 325 minus mu2. And we want to isolate mu2, right? We're trying to solve for that. So we can subtract 325 from each side. And we'll get negative 1.96. I'm just going to switch these around. Times 4.2426 minus 325 equals negative mu2. We want to go through and fix the signs. That will give us is a formula for mu, which looks like this. Mu2 equals 325 plus 1.96 times 4.2426. Okay. If you punch that into your calculator, you should get 333.3 repeating as our value of mu2. So that's the upper bound. That is the true population mean if our sample mean falls just on the bottom of the middle 95%, the middle alpha. So those are the two bounds: 316.7, 333.3. If it's outside of there, if the true population mean is outside of there, then what that means is our sample was really weird, right? Unreasonably weird. Okay, I'm going to just show you these formulas. Mu1 was equal to 325 minus 1.96 times 4.2426, and mu2 was equal to 325 plus 1.96 times 4.2426. We walked through this the whole way, just like we did with normal distribution problems and sampling distribution problems, in order to illustrate the fact that fundamentally these are the same. They're not different from stuff we've done before. Now, the thing is that these are the same as each other. Another way to write this, by the way, is mu1 comma, that's a comma, mu2 is equal to 325 plus or minus 1.96 times 4.2426. This right here is called a margin of error. So it's the sample mean plus or minus the margin of error. It turns out that if you do this type of problem over and over and over again, it always turns out the same. You always get a formula that looks like this. And this is why the formula the textbook gives you looks like this. It always turns into x bar plus or minus z sub alpha over 2 times sigma x bar, which if you want to rewrite that without sigma x bar, it can be x bar plus or minus z alpha over 2 times sigma x over the square root of n. It's always the same. But if you just see that formula, it's not so straightforward. The reason it's always the same is that we're always doing the same things. I'm going to scroll up so you can see as we walk through it what we'll be doing, what we do every time. What we do every time is we take a distribution, right? We block out our confidence levels area, right? Like 0.95 here. If it was a different confidence level, it would be a different area. We split that in half. So we put alpha in the middle. We split it in half so that this right here is alpha over 2. And then we use that to find a value of z. We do this every time, right? We take it down here. We use that to find the z value. So the shorthand for that is the z that has alpha over 2 between 0 and z. It's called z sub alpha over 2. That's what that means. That's just the value of z that gives you alpha over 2 between 0 and z. Right? Then once we do that, we plug it into the score formula. And when you plug it into the score formula, where am I? There I am. When you plug it into the score formula, you do the same math every time. I'm going to show you with symbols what it would look like. Right? So let's say we figured out our z alpha over 2. Right? And we wanted to set that equal to what? X bar minus mu1 over sigma x bar. We figured out all those things, right? We know x bar, we know sigma x bar, we don't know mu1. We figured out z alpha over 2. We're trying to find mu1. Well, every time you do this, what happens is the next thing you do is you multiply both sides by sigma x bar, sigma x bar. These cancel out. The next thing you do is you subtract x bar from each side so that these cancel out. And then you're left with negative mu1 equals negative x bar plus sigma x bar times z alpha over 2. You fix the signs, plus, plus, minus, and you get mu1 equals x bar minus z alpha over 2 sigma x bar. Okay? It doesn't matter what those values are. You're going to do the same math every time, which is where the formula comes from. It's just a faster way to get the same answer. But what you're doing every time is the stuff we were doing with the curves. Every time you do it, you're still basically using that intuition. Trying to find the mu's, right? You're trying to find the curves and the true population means that would make your x bar, the sample mean you have actually observed, just barely not crazy in one direction and just barely not crazy in the other direction. And if you do that, then you have your confidence interval. Okay, now another way to think about this is that, let's say we have a z. Let's just look at our score formula for a minute. We have sigma x over square root of n. Actually, let me erase that. Okay, so this is what the score formula looks like. And one way to think about this is that we have, if you're going to be taking a sample, okay, you're going to be taking a sample, you're going to get an x bar. That's going to happen every time, right? And if you know your sample size, which presumably you do, you know your n, it should be n, right? And you know your population standard deviation by assumption for now, right? You also know your alpha. Then you can just plug these things in. Essentially, every time you take a sample, if this is the true value, every time you take a sample, you're going to be off. And this z is like the offness, the weirdness of your sample. And what we're trying to do is we're trying to say we don't actually know the z-score of any given sample. What we want to say is assume it's not too weird, meaning it falls within alpha. What we can do then is we can say, well, what are the possible, what z-scores would we have? What z-scores would we get? Well, we get z alpha, we'd get negative z alpha over 2 and positive z alpha over 2, right? Those are the outside possibilities, right? Those are that's our interval in terms of z-scores. Well, x bar is fixed, right? That's stuck. Sigma x is stuck. Square root of n is stuck because we already took our sample. And so the only thing that can change between negative z over alpha, or negative z alpha over 2, and positive z sub alpha over 2 is mu x, which means that if we take these two values, those will kick out a mu x that's low and a mu x that's high. And if we do that, then that's our confidence interval, right? You plug in your two negative z alpha over 2s, and you know your two z values, and you get your two means. That's what those do. So that intuition is that every sample has a z-score, and we're using our z-scores essentially with our confidence interval, or with our confidence level, to get the population means that those would imply. Okay. Now, in order to do that, if you notice, we had to assume that we knew the population standard deviation. Now we can get away from that, and that's what we're going to do in the next video. So, this is how you find confidence intervals. The CI, when sigma x is known, looks like this: mu1 comma mu2, which is the two values, is equal to x bar plus or minus z, the z that corresponds to having alpha over 2 between 0 and z, times the standard deviation of the sampling distribution, which is the same as x bar plus or minus z sub alpha over 2, times the standard deviation of the population divided by the square root of the sample size. Okay, I hope that helps. If you have any questions, please let me know, and next time I'll show you how to do it when we don't know the population standard deviation.